Hello, and welcome to a digital statistics lecture for Salt Lake Community College. In this video, we're going to be going through section 3.5, the five-number summary and boxplots. I will say that there are three lists that we'll be using today in this video. The three lists are located on the last two pages. On page 20 at the top, you'll see 15 numbers. I have those in list 1. And then on page 21, you'll see two lists, one for name brand, one for store brand, and I have those in list 2 and list 3. Those are also given here horizontally. However, these are the exact same numbers as the ones above. So either have these ones here or have these two lists. But they mean the same thing. We'll be using those today. Now, 3.5 has to deal with the five-number summary, which was mentioned in an earlier question, and we've actually technically already talked about every number in the five-number summary. The five-number summary are 5 collected values that help describe how data spreads and the center of the data together. So it's a nice way to summarize the data in a relatively succinct manner. And it tends to really be good for skewed data, which is kind of a rarity. The five-number summary are values we've already talked about. They are the minimum, Q1, the median, Q3, and the maximum. So minimum, Q1, median, Q3, and maximum. Those are the 5 numbers in the five-number summary. And if you recall from doing OneVerstats, the last 5 values in OneVerstats are those 5 numbers. So we will have an easy way of calculating the five-number summary. You can do a lot of things with the five-number summary, including creating what we call a box plot. A box plot is a type of graph that's used to represent the five-number summary. And you can see a picture of a five-number summary and a box plot represented right here. Sometimes a box and whisker plot is called, or a box plot is called a box and whisker plot because there is a box here and then what we call whiskers that extend out from that box. To think about what a box plot does, it's basically 5 vertical lines and then connecting values in between. It's just a nice picture for it. You make 1, 2, 3, 4, 5 vertical lines, and then you connect the middle 3 as a box. This middle 3 here, this is your IQR, or your interquartile range, also as represented right here on the picture. So those tend to be the less resistant part of this graph. And then we have whiskers that extend out from that interquartile range out to the minimum and the maximum. That's what a box plot is. And the box plot also will sit above some number line that helps identify what each of the values are. Generally, that means creating one is going to be a lot easier. If you had trouble creating histograms or bar graphs as we had in Chapter 2, I think you'll have a much easier time with box plots here. Now, when you're looking at a box plot, you can also analyze the shape of it. The main thing you want to recognize is how long the whiskers are and how far away the max and minimum are from the median. So the median is always going to be the middle value in this data set. So maybe I'll do that in blue. So the median's right here, median's right there, median's right there. That will always represent where the center of the data is and is not really being pulled by the rest of the skew. Then you want to see how far the data spreads from the left and the right to that. So from the median to the left and the median to the right seems to be relatively equal, so we would say that's symmetric. Whereas on the second graph, the median to the right seems a lot shorter than the median to the left. So since the distance to the left is longer, it is left skewed. For the third graph, the distance to the left is shorter than the right. So since the right is longer, it is right skewed. You can usually see that by looking at whiskers as well. You can tell that the whiskers for the left and the right are longer for the left and right skewed respectively. However, sometimes that might not necessarily be the case, and you do want to check from the median up and down. So median tends to be your main key to go off of. Now, we'll also have what we call modified box plots. So this last note here is for what we call a modified box plot. And most statisticians care more about modified box plots than most. You'll also see a lot of questions asking you to create a specifically modified box plot. A modified box plot will identify outliers and separate them out with an asterisk. So this number out here would be considered an outlier. Then we have a new minimum. So new minimum. When you find, or in this case, I guess this would be a new maximum. Sorry. So new maximum. Because the old maximum was an outlier and wouldn't really be appropriate to represent with the rest of the data. We want the box plot to really represent how most of the data is represented or spreads. Now, the most important thing and the most common mistake with box plots that I see all the time, and I try to warn my students of this all the time, is that when you have an outlier, students will often separate those out, but the most common mistake is that they then use the fence, either the lower or upper fence, as the new minimum or maximum if necessary. Keep in mind that the fences were never part of the original data set. They were not there originally. Therefore, they should not be used to represent the data itself because they were not part of the data set. So do not use fences in your box plot representation. That's what this last note is here. If there are outliers present, the whiskers should only extend as far as the next largest or smallest data set that is not an outlier. So you see here that this graph has the fences represented just for your reference. The fences are there. But when an outlier, which is outside that fence, has been identified, we then use the next highest value as the most appropriate maximum. We do not use a fence as a maximum. And most times we don't even label this fence in the outlier or in the box plot itself. So do not use fences as minimums or maximums. Always use values from the original data set. We'll have a couple examples of that moving forward. But first, an example. Below are two box plots for the ACT score for incoming freshmen at two colleges. Use the box plots to compare the two colleges. So we have College A and we have College B. The 5-number summaries for each college. For A, you see going down, starts at 22 for the minimum. Then the next number is between 22 and 24. We can probably assume it's 23. The median goes to 24. Q3 is 25, and the maximum seems to go up to 26. Now, you shouldn't have to label each of these as min equals 22, Q1 equals 23. If you just list all of them in order, that is a good representation. You don't need to label each of them individually. Just having them in numerical order implies which one is which. Likewise for College B, its minimum goes to 25, it looks like. Q1's at 26. The median here is at 27. 30 seems to be Q3. And then the maximum is at 32. All right. Now, when comparing these, which college has a higher median ACT score? Well, we have our median of 24 compared to a median of 27. So that's pretty obvious. College B. There we go. College B has a higher median than College A. Which college ACT scores have less dispersion? Well, dispersion is supposed to be spread. So we can look at how long these are. College A goes from 22 to 26, so that has a range of 4. Whereas College B has a range from 25 to 32, so that's a range of 7. Just visually even, College A does not spread as much as College B does. So we would likewise say that College A has less variation than College B does. It doesn't spread as much. Which college is more symmetric? Again, looking at the graphs, this first graph definitely looks more symmetric. From the median up and down seems to be pretty symmetrical. But for College B, the median going up and going down is not really equal. So we would definitely say that College A is more symmetric than College B. And likewise, we would then say that college B is more skewed than college A. And in this case, we would say that college B is skewed, in this case, right. The distance from the median up to the maximum seems a lot larger. Alright, so that's just looking at box plots and being able to read them. Now we're going to take a data set, calculate our own box plot, and graph it. Consider the number of items produced per hour at a factory. So we have these 15 values. And I have those 15 values here in list 1. Let's just make sure I have 15 numbers. Okay, good. I've got all 15. Now to find our 5-number summary, we can go to Stat, Calculate, OneVerstats, run it on our appropriate list. In this case, we do not have a frequency list, so we'll leave that blank. We hit Calculate, and if we scroll down to the bottom, we should get our 5-number summary of 7, 21, 26, 28, and 30. All right. Now with that data set, we can also calculate fences. We can calculate our lower fence and our upper fence. However, to do so first, we should find our IQR. We need IQR, or interquartile range, to find that. The IQR is Q3, which is 28, minus Q1, which is 21, and we get an IQR of 7. So we should be able to find both our lower and upper fences. Our lower fence is our lower quartile, Q1, minus 1.5 times 7. These formulas coming from section 3.4. Remember, you don't need to memorize the formulas, just make sure you can find them. Should be on the second page of section 3.4. 1.5 times 7 is 10.5, so 21 minus 1.5 will give you 10.5. And then the upper fence calculation would be 28, the upper quartile, plus 1.5 times 7, which should give you 38.5. Before I move on, let's make sure my math is right there. 21 minus 1.5 times 7, and 28 plus 1.5 times 7. All right, looks good. So those are our fences. Anything that's below the lower fence or above the upper fence are going to be considered outliers. Now the data here isn't really as sorted, and you can sort the data if you want to, but if I just look at the 5-number summary, I should be able to tell if there's any outliers. My upper fence is 38.5, and since my maximum is 30, I don't have any numbers above 38.5, so this seems fine. So there's no high outliers, but my lower fence is 10.5, and my minimum was 7. So yes, there is at least an outlier. There is an outlier of 7. So 7 is an outlier. Since I've recognized 7 as an outlier, I should check to see if there's any other numbers that would also be considered an outlier. So basically anything below 10.5. After 7, the next highest number I see is 15, which is within the range of my fences, so that's fine. It would not be considered an outlier. 7 does seem to be the only outlier. With that in mind, we can draw our box plot. First, if we just draw the standard box plot, this is not a modified one, just a normal one, we're going to take all 5 of our values and we're going to draw that. The best way to do so is to draw 5 vertical lines for each of your values, so one per number in the 5-number summary, and do so above the number line. Don't do it on the number line because it starts to look really messy. First number 7 is right below 8, so I'm going to put a vertical line above where 7 is. 21 is around there, so I'm going to put a vertical line there. 26 is between 24 and 28. 28 is right there. And 30 is between 28 and 32. So 5 vertical lines. When you have those lines represented, you then connect the middle 3 as a box. That's your interquartile range. And then you have whiskers that extend out from that box. That's how you'd create a box plot. Remember as well, if you're definitely doing this by hand or even with a calculation, you should have some appropriate title up here and you should also have some appropriate axis title down here. So always try to make a graph stand on its own. Looking at this graph though, this part of it really looks ugly. That's kind of gross. You don't want a box plot to extend that far, particularly when the rest of the data seems much more together. Much more of the data seems up here. So what we'll tend to do instead is create a modified box plot. The modified box plot is going to take any outliers and represent those with an asterisk. So our outlier 7, as we identified earlier, I'm going to identify with an asterisk. Then, since that was my minimum, I need a new minimum in this box plot. My new minimum is not going to be 10.5. That was the fence. My new minimum, so I'll say new minimum is going to be the next lowest value in the data set. If you look back at our data set, we even identify that the next lowest number was 15 after 7. So our new minimum is likewise going to be 15. 15 is roughly here, so we'll put a new line for it there as our new minimum. And then all the rest of our values from before. 21, 26, 28, and 30. So you got your box and your 2 whiskers. That box plot looks a lot better to represent the majority of the data. With that one separation of 7, which now even looking at it graphically, you can definitely see that 7 seems very strange compared to the rest of the data. And again, remember, title, an axis title of something. Just make it appropriate, make it clean, easy. Doesn't need to be overly complicated. Something like in this case, maybe it's just items produced. So I would maybe say for my axis title, just something like items. And then maybe a title being like factory production. Something like that. Doesn't need to be overly complicated, just something neat and clean so that you should be able to look at a graph and understand what it's talking about, at least to some extent, without looking at the original paragraph of description. Okay. Got one more page to go through. This exercise, I have both these lists again in list 2 and list 3. Do store brand chocolate chip cookies have fewer chips per cookie than Keebler's Chips Deluxe chocolate chip cookies? To find out, students randomly selected 13 cookies of each brand and counted the number of chips in the cookies. So we have the name brand and we have the store brand. Okay. So those are also given here, and they're given in numerical order in case you want to do this by hand. A. Determine the Five-Number Summary for each brand of cookies using the TI-84 or by hand. So I'm going to use a TI-84 here. So I'm going to do stat. I have these in L2 and L3, just checking. Stat, calculate, go to one-var stats. And first I'll do it for the name brand, which is in list 2. Right? Yep, name brand is in list 2. Once I have, stop moving. Once I have all that entered, go down here, and I have my Five-Number Summary for name brand as 22, 23, 26, 30, and 35. I then can do stat, one-var stats, and run it on list 3 to get the Five-Number Summary for that list. My values there will be 15, 20, 24, 27.5, and 33. Alright. Now, both of those are created, and what we want to do is create box plots for both of these graphs. Now, it doesn't ask us to check for outliers, but I'm pretty sure that there are no outliers in this anyway. Just looking at these, it doesn't really seem like there are outliers, but if you want to run the fence calculations to check, you should be able to confirm that there are none. I think that if there were any in the 40s or below 10, there would be a question of outliers, but I don't think there are any here at all. So we are just going to draw the side-by-side box plots. To draw a side-by-side box plot, what that literally means is that you put one box plot over another. We actually saw an example of this with ACT scores 2 pages prior. For name brand, we have a minimum of 22. So again, remember, just 5 slashes. 22, 23, 26, 30, and 35. Those 5 slashes should be enough for name brand, and then you can connect them as a box and whisker plot, or a box plot. The reason why I'm trying to get away from box and whisker plot is because box and whisker plot has a bad implication. It tends to imply that there are always whiskers in box plots, but there can be some really weird ones that you make where there are no whiskers. And that would happen when, for example, the minimum and Q1 end up being the same thing. Then you end up just having a box plot that looks like this. So you might not always have both whiskers. Sometimes you'll have none. It depends on what the data looks like. So box plot is a better way of describing the data. For store brand, we have 15, so 15 is roughly here. 20 is there. 24. 27.5 is there. And 33. And then, again, connect the box in the middle, and then whiskers to the outside. There you go. Now, overall, this graph looks okay. There's at least labels here for the side. That's good. But we should have values on the bottom. So I'll say cookies. That's what these values are. How many are these, cookies or chocolate chips? Chips. Okay, so these are chips. These are a number of chips in the chocolate chip cookies, and then maybe just chocolate chip cookies as a title. Something like that. Again, doesn't need to be overly complicated, but just put labels. I will also say that some people do like to put labels above their box plots, so sometimes they like to label 15, 20, 24, 27.5, and 33 above the values for the box plot, and that's fine. That adds more labels and it's easier for the reader to analyze. There's nothing against that. So if you want to do that for box plots, you can. Now, looking at these, does there appear to be a difference in the number of chocolate chips per cookie? Overall, the medians seem pretty close to each other in terms of where the majority is, but there's not as much of a difference. We do see a large difference in minimums between the datasets, but overall, the datasets do not seem too terribly different. Important to note, though, that store brand seems more symmetric, whereas name brand seems, in this case, skewed right. Whoa. So that's probably how I would analyze this. Like the data sets overall, where some of the values are, there's not too much of a difference. It's just like a little bit off. There is like some difference between the two, but the biggest differences would be between the minimums. The minimums here seem to be significantly different from each other, and also the shapes of the graphs. Store brand definitely looks very symmetric, whereas the chocolate chip cookies for name brand seems to be more skewed to the right. Last one, C, does one have more consistent number of chips per cookie? We basically just answered that. But yes, the store brand seems more symmetric than the name brand. And since it is more symmetric, would thus tend to be more consistent in terms of how many chips are in the cookies. Name brand. There we go. All right. With that said, though, that's everything in 3.5, and thus also everything in Chapter 3. With that said, you should be able to complete all the homework for Chapter 3 as well as any video activities if those are in your class. If you have any questions, feel free to put those in the comments below or ask your instructor. But with that said, I hope you have a nice day.